AstronomyCast, episode 260 for Monday, April 9th, 2012, the technology of lasers and masers. Welcome to AstronomyCast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Everettsville. Hi, Pamela. How you doing?
I'm doing well. How are you doing, Fraser?
Doing great. So I wanted to give a big shout-out to a piece of technology that we've had for a little while, but I had never directly used it, which is the AstronomyCast app, which my kids love to listen to AstronomyCast. It's what they go to bed to every night. I'm not sure whether
creepy.
I don't think a lot of it is getting retained, so every now and then I quiz them, but I guess they like to listen to our voices, which I think is adorable.
Okay.
So, and I decided to give them the app because it gives the access to the entire catalog, and you don't have to download it and install it on your iPhone or whatever. I know there's a lot of people out there that like to listen to all the back catalog episodes of AstronomyCast. And I also had gotten a few complaints from people that some of the old titles weren't in. So I went back and fixed everything. So now it should be really tight. All of the episodes are there. You can get all 250 plus episodes and just play them all instantly through our iPhone app. And I think it's $1.99 for the app itself.
Yeah, it's something completely reasonable, and what you're paying for is someone other than us wrote the app.
Yeah, that's exactly right, and it's done through our audio hosting provider. But it's really convenient and a really good way to get access to our entire library of episodes, and I highly recommend it. So do a search.
Download it.
Yeah, do a search on iTunes for AstronomyCast, and you should find our app and install it, and I think you'll like it. The only problem is that it never stops playing. So once you start it, I sometimes I'll come in and it's like 4 in the morning, and the kids have been had the thing going on,
there's a
burning through their batteries.
solution for that. If you use, there's a timer on the clock. I do this all the time. I don't listen to AstronomyCast like this, but I do this for other things all the time. I'm not that creepy. But if you use the timer on your clock setting on your iPhone, set it to 20 minutes, turn off iTunes. It will also turn off apps like ours or Audible.com's app or the public radio player or all these other players that are out there that allow you to listen to droning voices as you go to sleep.
I've got I know we're recording right now, and sorry Preston, but actually I've got a sprinkler that's hitting my window and adding a lot of noise to my audio. So I'm just going to go fix that. I'll be back in 1 second.
Okay, so while he's off doing that, this is the most crazy day of attempting to record. So we've now hit the point where we're normally winding up, and it's okay if a sprinkler is hitting his window. But he's going to go shut that off. I'm going to go find our comments thread. And I see a few of you on Twitter, and I'm really grateful for that. If you want to ask questions while I drone, yay, there's people out there. Hi, all of you who are leaving us comments. Oh, John has to tutor a student. We're sorry, John.
Okay, there we go.
Okay.
Let's get on with the actual recording. So here we go for that part.
We probably want to start over the recording.
Why? You can just cut it out.
That's true. Okay, sorry, Preston. We're going to torture you.
Yeah. So just when you think you understand it, light will do some amazing things. Just look at the discovery of lasers and their use in almost every technology that you can think of, from cutting to transmitting information to, yes, astronomy. And nature has figured out its own version of laser technology called the maser, which has kept astronomers puzzled and excited for years. So I guess this week we're going to talk about the actual underlying technology just to help people understand the physics of how lasers and masers work, and then we thought next week we would actually go into its various applications in astronomy. So, and I really resisted the urge to talk about sharks and lasers. So, what is your...
So did I. We're both horrible humans.
No. We just can't go that way. So then let's talk about lasers. So what exactly is a laser?
It is, and laser technically is only optical light, but we're going to, throughout this episode, end up interchanging using optical light, using infrared light, and all of these things. What we're talking about is a process by which light is amplified. So laser is a light amplification process, which means you start with one photon and you end up with a whole lot more than that one. So the whole acronym is light amplification by stimulated emission of radiation, which sounds like you're doing something really dirty, and really it's not. So to break down all of these separate words, so let's start with the stimulated emission. Stimulated emission means that you have in your atom, normally your electrons like to hang out at the low energy levels, but if you get them excited, they'll jump up into higher energy levels. And stimulated emission means you have an electron hanging out at that higher energy level, and along comes a photon and it interacts with that atom. And if the photon has the exact same energy as the transition of that electron from the lower to the higher energy level, for a lot of complicated quantum mechanical reasons, the fact that that interceding photon and that existing energy jump are exactly the same will cause the electron to spontaneously jump from the higher level to the lower level and sympathetically give off a photon of the color of the original photon that's in the exact same phase, and so you end up with coherent light as a result of one photon triggering the emission of a second photon.
Right, and I understand this part, that essentially you're getting more of the same flavor of photon. You're going to get the right wavelength, and you're going to get a very, and so these photons are going to come pouring out in the exact same color, right? Right.
So you have radiation initially, that's your incoming photon, that's causing stimulated emission between those two different energy levels, and the light amplification part means you start with one and you end up with two coming off on the other side.
And now radiation sounds scary.
No,
when they
so
mean
light
radiation.
Is radiation. And
right.
Radiation is the most abused word in science in a lot of ways. That and theory. Theory gets even harder than radiation. But if I shine a flashlight on you, I'm radiating you.
With visible light.
With visible light, which
right.
doesn't hurt you unless it's really intense.
Really intense light. Right, okay, so you are radiating, and then you are then you're emitting photons, kind of like copies of that first photon.
Exactly, and so the actual hard part about this is electrons don't like to hang out in that higher energy level. So most of the time we don't end up with lasers. So the fact that there is light coming out of the light bulb in my ceiling is not causing stimulated emission all over this room. The gas in this room is not lacing me on a day-to-day basis. Otherwise, life would be difficult. So in order to get lacing to occur or masering activity to occur, the physics is the same no matter what the color of the light coming out of the system is. You have to somehow get what's called a population inversion. This means that you have more electrons hanging out in this higher energy level than in the lower energy level they'd like to be in. Otherwise, what's going to happen is you have an excited one up here, it collapses down, gives off a photon. That photon doesn't go very far before it hits another electron in the lower energy level and jumps back up, and you simply have absorption and emission processes going on. If, in fact, you have more electrons in the lower energy level than the higher energy level, you're actually going to end up absorbing the light at the end of the day. So the only way to end up with extra light coming out than you had going in is to start out with more of the electrons excited than not. And that's not a normal situation.
But I think that explains the color of the laser, but what explains the shape? I mean, when you fire a laser beam, it has a very significant, very straight shot that it takes.
That has to do with the mechanics of how they build the system. So the easiest example is the pulsed ruby laser, and this was one of the first lasers ever built. And so basically, you take a synthetic ruby core, wrap it with a mirror, put a mirror on one end of it, so you have this ruby cylinder. Wrap mirror around the long part of the cylinder, put mirror on the end of the cylinder, and put partial mirror on the other end of the cylinder. And what ends up happening is you end up getting the stimulated emission going in all sorts of different directions, but the only time the stimulated emission is allowed to escape is when it goes out the one end that isn't a pure mirror, and the rest of the time it's just triggering more and more and more of these transitions to take place. So what ends up happening in one of these ruby lasers is they wrap it, so think one-way mirror. So they wrap the laser in the mirror and then wrap the mirror and laser with a light source that flashes. When the light source flashes into the ruby crystal, the electrons jump to higher energy levels. They're now in that higher energy level, and when one starts jumping, it causes all the rest to start jumping, and so this is what stimulates the emission.
But they can only escape in that one direction that you haven't wrapped.
Right. So that simply becomes a geometry problem.
Right. Okay. So it's not like a function of the way a laser works, just in general.
No.
And so if you hadn't wrapped the laser in this mirror, would you just be getting this color light just going out in all directions?
Kind of. Now the trick that isn't having to do with the fact that you wrap the sucker in a mirror is the fact that the light is coherent. This means that one photon's wave lines up with the next photon's wave, lines up with the next photon's wave, and so the light interferes coherently. This coherence is actually triggered from the fact that each of the stimulated photons picks up the phase of the photon that's stimulating it. So that stimulated in-phase coherent light part, that has to do with the fact that it's a laser, not the fact that you shaped the beam coming out. This is why flashlights, which also have mirrors, are never going to be the same thing as lasers.
Right. And also, I mean, they're just not giving out they're giving out light in all colors, not in that one.
Right. Well, you can have a diode flashlight, and a diode flashlight is all one color of light if it's well made, but the light's not coherent. This is the special thing about lasers, is if you could stop all of the photons and somehow actually see the wave, and you can't do this, quantum doesn't let you, but you can measure the interactions. And when you do this, you find that all of the maxima of the waves and all the minima of the waves are politely lined up in a coherent way that allows you to interfere the light with one another. If you take a diode flashlight, stick it through a spectrograph, you're going to see that nice, it's all basically one color, just like lasers are all basically one color. But even though you have that one color, the photons are all scattered all over the place in terms of how the maxima and minima are lined up. So it's incoherent light.
Right. Okay. And so where did the discovery of lasers come from? And I know that MASERS plays into this, right?
Well, it's a long and storied history that it's interesting if you start poking around the internet trying to figure out the history. You can see national biases in who wrote what, when, and the Wikipedia article in particular shows definite national biases. So the idea for a laser can actually be tracked back, like many other things, to Einstein, who basically started to understand that stimulated emission could occur. This idea that you have an excited electron, a photon comes along at the energy of the gap between that electron and its next energy level. This triggers a coherent photon coming off. He was the person who first figured that out. And it wasn't until almost 40 years later that various scientists working on a number of different projects started to figure out how to make this happen in a laboratory. And what's kind of interesting is the first group to do this. It was a pair of fellows, Basov, Towns, and a trio of fellows, Towns, Basov, and Prokhorov. And I'm sorry for the deadly pronunciation on that one. They were working on trying to stimulate emission in molecules, and they'd spend a bunch of money on it, and there was a bunch of people complaining, and I'm looking at the numbers, and I can't take my eyes off of them because it's so funny how the scale of things have changed. So working back in 1954, there was a group of people who were trying to close down their research because they'd spent so much money, $30,000. They'd spent so much money.
How could they spend that much money?
I know. And everyone just saw this as a horrible waste. What was the purpose? And so when they finally got a working apparatus, they called it the MASER, the Microwave Amplification by Stimulated Emission of Radiation, MASER device. But the folks who were mocking them, who didn't see a purpose for this, said that MASER actually meant means of acquiring support for expensive research. And I just love the way scientists find to mock each other. We are not a friendly work and play well with others profession all of the time. But this initial work in 1954 was really what started it all. And like so many other things in science, it's so much easier to work in the longer wavelengths, in this case the infrared and microwave wavelengths. And over time, scientists were able to figure out how to build things that extended to shorter and shorter wavelengths. So it started with them, then moved on from there. And it was only after that 1954 discovery that we were able to finally start picking up, and I'm sorry, I'm trying to figure out where my dates just went. This is where everyone realizes Pamela does not know dates. I'm sorry, Preston, you're going to have to edit this while I try and find the slide my dates are in. This is the first time I think this has happened while we were recording in a Hangout.
I know. We had our act together.
We did, and then I blew it by losing a slide. Okay, found it. Okay, so returning back to where we were. So in 1964, the first laboratory maser was developed, and despite all the demeaning that these guys got, they went on to get the Nobel Prize for their research. So I think in the end they got their comeuppance. They got mocked, they got ridiculed, they got a Nobel Prize. I call that a good day.
Yeah. See if you can work the Nobel Prize into the acronym for lasers somehow.
But it was just a year later, in 1965, that the first natural maser, and we'll be talking about this more in the next episode, the first natural maser was found in the Orion Nebula. And since then, people have been steadily working to try and get better and better at building both masers and lasers. So it's been a long process, but from that 54 maser to 60 optical to 65 Orion Nebula, we've been steadily making progress on developing these things one at a time.
And so, you know, I've got a laser in the house that we play around with sometimes, very carefully. It's very dangerous and terrifying, actually. But I guess what is the technological advances that have gone from that original microwave? I mean, now we're at what, petawatt lasers? I mean, the technology's gotten pretty amazing. What are the technological advances that have brought lasers forward?
Well, we've been working to try and figure out what are the different ways to create an environment where the stimulated emission can take place without having to put too much different energy into the system, because this is an energy-intense process, and the energy you put into a laser is not all going to come back out as the laser beam. So what we actually have to do quite often is not just bump those electrons up one energy level to create this population of electrons ready to cascade down with stimulated emission. But what actually ends up happening is you have to pump energy into the system to jump the electrons up more than one energy level. They get up into this higher unstable energy level and then drop down into a lower semi-stable energy level where they're happy to hang out until that photon comes along and stimulates emission. And what we've been figuring out are what are the most efficient transitions, how do we manufacture gases, dyes, crystals, all these different substances that are capable of being maintained at that higher energy level. How do we build things that are stable so that we're not breaking our crystals? It's mostly been just technological revisions over the time and trying to figure out the material science of building purer and purer materials that get us to the different types of transitions that we want to get to.
But essentially there are these perfect transition points where you both can get energy in and the way the photons come back out, and I guess if you don't hit that transition perfectly, you're going to be like wasting energy and heat and things like that?
Well, it's more a matter of trying to figure out how to do things so that you're not spending too much time pumping. This is something that can only be done in a system that's not in equilibrium. If you have a gas that's happily hanging out in equilibrium, it's always going to have more electrons in lower energy levels than higher energy levels. So you have to constantly be pumping the system with energy to get things higher up. Now, if I'm in a system where I'm pumping things up and they immediately cascade back down, that's ineffective because something might naturally cascade down to a lower energy level before that photon can come along and stimulate emission. So I want a system that's stable enough at that higher energy level that it has a chance to be stimulated before it naturally collapses to the lower level. So it's a matter of we have to figure out how do you get electrons into those semi-stable places waiting for the stimulated emission. Then once they're there, you have to figure out how do you build the system so that everything's nicely and politely focused. And how do you not melt things in the process, and so the not melting, not blowing up. These are all the same sorts of problems in some ways that you're figuring out as you're building faster and faster processors. These are hot systems that have to be maintained very precisely, and if they're not, they melt, and that's bad.
Yeah, and so what are the limits then? I mean, if we're just looking at anywhere along the electromagnetic spectrum, could you make, I mean, a maser is a microwave, right? Could you go to longer wavelengths? Could you make a maser out of the longest wavelengths of radio light?
Well, so there it becomes a problem of long wavelengths, particularly long wavelengths. It gets kind of hard to contain that in a cavity where they resonate nicely. So the containment vessels that you're using to build your lasers in are actually related to the color of light that you're using. And as the radio gets too long, so if you start looking at the longest imaginable colors of radio, yeah, you could, but would you want to? Because you're starting to get into big systems. And then on the really short wavelength, you start running into different sorts of, that gets really hard to contain issues for building the resonant cavities.
Well, I know you can purchase blue, I've got a green laser, and I'm sure most people have had red lasers. I mean, my kids' Nerf guns have a red laser on them. And you can buy blue lasers, and I think you can even buy violet lasers now, which are terrifying.
It's really kind of amazing. Scientists are slowly discovering that if you try hard enough, you can make almost anything undergo stimulated emission, make almost anything lace. And this means that if we work hard enough and are willing to throw out enough energy, we can create just about any color just by using the correct materials to find those transitions that get just the color that we're looking for to be emitted. Now, it does start to run into matters of you can do something and have a wussy laser fairly easily, but as you want to focus the laser better, as you want to get higher power energies, it gets more and more difficult.
Could you, I mean, are there ultraviolet lasers?
Yeah.
Yeah, there are.
You can, it's just a matter of finding the right materials. And so there you start looking at things that are doped with a variety of different metals. You're looking at rare earth substances. We've built lasers that go all the way out to 120-ish nanometers. So yeah, we're getting out into the ultraviolet, no big deal. We get out into 1 millimeter wavelengths, no big deal. Well, it is a big deal, but we can do it. That's what's so awesome is we have the technology to span from the mid ultraviolet out to the far infrared in laser light nowadays.
And theoretically then you could even go into X-rays.
That starts to get into containment issues. So here it's how do you build a resonating container that allows the pulse or the pumping energy in but doesn't let the X-rays back out. You're trying to get things to go to a higher energy level to start with, and X-rays are already pretty high up, so you're looking at most things are going to start ionizing there. So X-rays becomes technologically extraordinarily challenging. This isn't to say it's impossible, it's just sort of to say, yeah, that gets really difficult, we haven't got there yet.
Now, why would we want to use different wavelengths of laser light?
Well, it all depends on what you're trying to do. So there's all sorts of different applications for lasers. From, let's do something simple like at the grocery store, scan that barcode with the red light that's perfectly safe, sort of, kind of. You still don't want to shine it in your eye. Anything that is more powerful than 1/10 of a milliwatt is bad. So, but for the most part, the reflected laser light of the beam on the grocery store thing is fairly safe. So that's a way of speeding out the checkout process. You scan a laser beam across it, you look at how the light is reflected back by the white and black bars, and suddenly your checkout clerk doesn't have carpal tunnel disease as bad as he or she might have a few years ago when they were typing all the numbers in by hand. Then with astronomical technology, we use lasers to actually ionize patches of gas in the upper atmosphere. So we need a color of light that is tuned to triggering those ionization processes, and then we focus our telescopes on that ionized pocket of gas. So that's a completely different color, a completely different purpose. In medical lasers, they actually have lasers that are tuned to the point that they're able to eat away just fractions of a cell at a time. And in the process of doing this, they reshape the lens of your eye, which I think is a terrifying process.
Yeah.
But people undergo this every day, every hour, all around the world, and for the most part, nothing bad happens.
Right. We look at like Blu-ray lasers.
Yeah.
It's about being able to have the size of the information that you're trying to read. You're trying to match up the wavelength of your laser with the size, I guess, the density of the information packed onto your disk.
Hey, sorry about that.
You're back?
Yes. Can somebody please out there confirm that we're still going live? Actually, I can probably confirm that we're still going live.
Scott just said we're back.
Okay, good. Cool. Sorry about that, everyone.
And what would happen, Scott, if you can answer, what did you see when we disappeared? Anyway, interested to know when Pamela disappeared, what happened to the live stream.
Yeah.
Now, I just left the recording going, so why don't
Yeah, I did the exact same thing.
Okay, all right.
Okay, so I was talking about lasers in astronomy.
We were talking about, and then I mentioned that, did you hear me talking about Blu-ray lasers?
Blu-ray, right.
Yeah.
So you were in the process of talking about Blu-rays when the world ended.
Yeah, so why don't I'll just re-say that, okay?
Okay. Sorry, Preston.
Right, so blue lasers are just an example where you're matching up the frequency of the laser with the density of the information that you're trying to read, right?
Right, so when we go from using CDs to using DVDs to using Blu-rays, in each of these instances, we're using shorter and shorter wavelengths of light, and that in turn allows the bits of information to become smaller and smaller and smaller. The different wavelengths, they are also getting smaller, and so we're packing more stuff closer together. It's also allowing multiple layers of materials to be used, and it starts getting to lots of complex materials processes, and it just has to do with shorter wavelengths means things packed together closely.
Right, but you can imagine that situation you mentioned earlier, right? You've got your great big barcode scanner, and you've got the laser slowly going across that barcode, and then it's reflecting light back to a sensor that's detecting the changes. And then if you wanted to, you're going to get those differences in brightness and dimness that's being detected, and so it's kind of the same thing with the way a laser is shining.
Yeah.
A blue laser shining on a very small, the pits on a Blu-ray.
Yeah, no, the DVD
back out.
Yeah, it's exactly the same in this case, where it's at hundreds of times a second, going on off as your DVD spins or as your CD or Blu-ray spins. And so you have to very, very precise mechanics to figure out exactly where they are on the CD, DVD, or Blu-ray, which is why they die so easily and violently.
So then what do you think are the future limits of laser technology? Where's this all going to go?
I'm not sure that the limits can actually really be defined if we're allowing ourselves to pour in as much energy as we want. One of the most amazing things that's currently going on with laser technology is there's folks at a variety of different facilities, including the National Ignition Facility, National Ignition Research Facility, are trying to create fusion using lasers. So they're focusing lasers down to a single point on a glass bead that's doped with a variety of different materials and trying to get fusion to take place in this glass bead when a pulsed laser that's petawatts in power. So we're looking at like all the energy of New York City condensed down to a single point. Yeah, it's kind of
a fraction of a second.
amazing. And these systems use capacitors that are so large that they're in special cooling material in Olympic-sized swimming pools. There's a variety of these places being built around the world, and they're awesome. So here we're talking about lasers in places that you could have sharks swimming around the capacitors used for the lasers, except they'd all die when you fired the laser, so we won't actually do that. And we lost Fraser. This is the most cursed episode ever. If I were superstitious, I'd be saying that clearly the universe does not want us to discuss MASERS. It's a conspiracy where Google Plus is trying to end this. I'm not sure what happened. Scott, can you still see us? Can you chat at me if we're still here? Hello? I feel like I'm talking to an empty room, giving a chat at a blackboard with no one listening. But according to my statistics, there's 34 of you still out there. So hopefully, Fraser will come back. I know I had to switch from Google+. So Scott is saying that we are live as I blather on to you empty-headedly. So since I'm in the process of waiting for Fraser, the problem I ran into when I crashed was I had to actually switch from using Safari to using Chrome. There he is. So hopefully he didn't have to do the same switch. Did you have to switch browser types to get it to work?
No. Was I the one who got cut off this time?
Yeah.
Yeah. All right. I don't know why technology failed. I got nothing.
It's the cursed episode.
It is the cursed episode. I can see that we're nearing the end. We've just got to get through to the end of this episode. So I asked you a question. You were talking about fusion, how cool it was to get the power of New York City. Then
right,
what did you
right.
say?
So
because I didn't hear the rest.
So these are basically lasers so big that you could have sharks swimming around the capacitors used to power the lasers, but you wouldn't want to do that because when you fire the lasers it would kill the sharks, and that's bad. But they're still giant, awesome lasers.
But so in other words, you somehow managed a way to sneak a sharks and lasers reference into this episode.
It was required.
It was required. It was destiny. Cool. So I guess the last thing I want to talk about is lasers on spaceships,
yes.
shooting other spaceships in space in the far, far future.
Well, yes, you can do it. There's actually folks working out at the NASA John Glenn Research Institute on lasers of destructive powers. So there's pictures you can find of lasers that have hit things and melted them and done bad things to them. There are people who are working on this, but it's huge amounts of energy. You're actually much better off with artillery. So
right, throwing rocks.
Throwing rocks at the end of the day is the best way to get the most bang for your input energy.
There was a classic quote, and I'm sorry I'm going to mangle it because I don't have it sort of in my brain, but essentially it was like back in the 1980s when they're working out the Star Wars technology, and one of the directions they went down was to figure out if they could come up with laser weapons to actually shoot down missiles.
Right.
And at one point, I forget the total amount of energy that would be required. It would be like 10 to the power of 20 or something like that, joules of energy to do it. And they've been able to push lasers to the point that they were 10 to the power of 10 joules. And so when someone said, "Oh, so we're halfway there." No, not halfway there.
No,
No,
exponentials do not work that
yeah,
way.
one tiny fraction of a fraction of a fraction of the way there. So you don't see in the far, far future, I mean, with the kinds of energy you need to pour into it, the difficulty in containing the emissions as you're trying to or build up the actual coherent beam that's going to come out, you're going to irradiate your everyone on your spaceship in the bad way to try and get things to those energy levels.
Well, it doesn't make energy sense. You have to put so much energy into the process that you might as well be flinging a rock, because it can retain more of the energy. Now, where it does start to make sense to have lasers in spacecraft is as communications devices, because you can send a fairly coherent beam huge distances. This is why we're spotting masers and lasers in space at cosmological distances. So you can potentially use these as communications devices rather than as war devices. So there's a future for lasers on spacecraft.
All right, cool. All right, well, thanks a lot, Pamela, and we'll talk to you next week.
Okay, bye-bye.
I'm going to stop this cursed recording.
And save it quickly.
And save it. Though I don't even know why I should.
Because Preston will put it together and it will be fine, because Preston is awesome.
Yeah.
So when you donate money to Astronomy Cast, which we encourage you to do, you are paying Preston. This is what the donations to Astronomy Cast go to, is paying Preston to make us sound good. And we love it when you donate, because then we can pay Preston. And yes.
Perfect.
And you're also paying for the transcripts, which are done by another wonderful lady. You're paying for the show notes, which are done by Nancy Atkinson. So Fraser and I are doing this for love. The people who are making our website go are doing it for money.
And love.
And love.
All right. I'm afraid to even look for questions. So just sort of fair warning, we'll take on some questions until our internet falls apart.
Yes.
That's, I think, the best we can do until this hangout is destroyed.
Okay, so how about laser swords from Maxim?
Laser sword, some kind of saber made of light?
So the problem with that is when they clunked together, they would just pass through each other, and that's really not exciting.
But I guess the question is, would such a technology actually be possible?
A coherent laser beam?
That stopped.
No, it's the stopping part.
Yeah.
That requires a mechanical device. I mean, in theory, you can use a Fourier transform to generate a bunch of different colors of light that are interfere in a way that gives you a beam that's fine for a set distance, and then interferes to subtract everything out. After that, this gets really, really complicated. In theory, you can end up, but not for a noticeable distance. That's just crazy talk.
So you're saying that you could put out the photons in such a way that they form a shape.
Yes, you can get so. One of the things that comes out of Fourier theory is all waves can be combined and subtracted to create longer wavelength type things. So when you study variable stars and you get these crazy shaped light curves, you do Fourier analysis to figure out what combination of sines and cosines can be used to create the shape that you see the star making. So in theory, you should be able to combine enough sines and cosines in order to get something that has a pulse size and then stops. So to get this single coherent pulse of light. Now, I don't see that happening.
Right. Okay. And so you would probably need some kind of magnetically
contained plasma.
Yeah, you'd need to have some way that you're controlling an endpoint out. Anyway, it sounds really hard. Just shoot them with a gun.
Yeah. Yeah. Seriously, that's the way to go in the future.
Yeah. Same problem. It's always the same problem with lasers. You know.
Yeah.
If you want to use them as weapons, really, there's much easier ways to do this. Now, I am afraid to look for questions. So, do you have any more questions, Pamela?
So Scott Lewis said, "Who out there divided by 0? I want names." I do too. I'm afraid it's a programmer. So let's see. Nicole asks, "Is Mercury in retrograde?"
That's what it is. Mercury's in retrograde. No wonder we're having a difficult time.
Dr. Evil is rubbing his hands together. Cursed but interesting. I'm seeing lots of comments on our tech fail versus asking questions about the science. Oh, someone wrote, meh, blasters are way cooler. Yes, blasters are cooler. And blasters, we can figure out. That's just a pulsed laser. We know how to do pulsed lasers. Again, not so efficient energy-wise, but yes, fun.
And then we've got one question here from Andrew. So it has nothing to do with lasers. But
okay.
You talked about Jupiter
more than I did.
Being an asteroid sweeper for the solar system, and it's conceivable that they swept up massive items over the course of history. What happens to the matter of those items when they enter Jupiter's atmosphere?
So Jupiter is a really thick, really hot atmosphere, so it's going to generally cause most things to burn up, to basically heat up, melt, fall apart, get destroyed, and then that material just gets incorporated into the atmosphere of Jupiter. So the heavier weight stuff, it's going to fall through, it's going to become part of whatever the core of Jupiter is, and we don't really know. We're still working on figuring that one out. Some of it's probably going to end up becoming part of the atmosphere of Jupiter. It's the exact same process that basically happens when things burn up in the Earth's atmosphere. Most of it burns up and you see this trail of light, which is the heat energy being given off in the atmosphere. Some of it makes it to the surface as shards, while in Jupiter the shards just go a little bit further.
Yeah, and we had a situation that showed us what this was going to happen, like in grim detail, when we had the impact of comet Shoemaker-Levy 9 crash into Jupiter at high speed, at cometary speeds, and you saw these gigantic bruises and bright flashes that happen on the surface of Jupiter. So, and
this was just material splashing up from lower depths that we normally don't get to see.
Right, but you were having impacts, fairly violent impacts happening. I mean, whatever, the comets were pulverized when they hit the atmosphere. It's not like they gently splashed in and
no, and there were fireballs.
Yeah, they went kapow and
ate the internet. I don't know if Fraser's going to come back. I'm going to see if I can get him in chat. We have fought the good fight for about an hour here. Oh, he's completely not online at the moment. Death, looking at Skype. You guys have been a wonderfully patient audience. I see that there's 42 of you out there suffering with us. Looking for Fraser via other technologies. Oh, I think the internet completely ate him because I don't see him on Skype either. Wait, he's back. Maybe. Sort of. I got a little message at the top of my screen that says Universe Today is online, but I'm not seeing him anywhere else. Okay, I'm going to look and see. So Carolyn, with a complicated last name, wrote, she's quoting from a website here, light normally travels in straight lines, but physicists have known for several years that superimposing a pattern on a laser beam can make it bend. You can also use magnetic fields to make a laser bend or gravity to make laser light bend. But I'm now hearing from Fraser, unfortunately, that he's not going to be able to make it back in. So at this point, I think I'm going to give up fighting the good fight. We are going to try and do more recording. I'm not quite sure when at this point. I will be traveling for the next several days. If the internets are benevolent, we may try and do something this evening or one of the other evenings this week. We will, as always, keep you abreast of details on Twitter. You can follow everything that we do at CosmoQuest X on Twitter, or follow CosmoQuest on Google+, or follow myself, Pamela Gay, or Fraser. You can also follow our pages, CosmoQuest, Astronomy Cast, and Universe Today, and we will try and keep you up to date with everything that's new in astronomy. The next scheduled for certain hangout is going to be Wednesday at 4 p.m. Pacific, 7 p.m. Eastern. If you subscribe to our newsletter, we'll send you all the different time zones around the world. And that's going to be the weekly science hour, this week hosted by Emily Lakdawalla from the Planetary Society blog. She's going to be interviewing a as-yet-to-be-announced scientist about something new in planetary science. So I encourage all of you to join her. And thank you so much for dealing with all of our chaos this week. Bye-bye.